Lecture 20 covers section 6.3.2. At the end of today's lecture, you should be able to solve statically indeterminate systems using the superposition method. Within statically indeterminate problems, one or more supports is redundant. That is, there are more support reactions than are needed to maintain static equilibrium. Thus, we cannot solve for our reactionary forces due to our equilibrium equations. Now, we can treat this redundant reaction as an unknown by eliminating the support. But we must consider the deformation produced by the support to ensure compatibility with the original problem. If we consider separately the deformations caused by our given loads and by the redundant support, and then add them together, we can obtain a solution for our reactionary forces via superposition. Let us look at an example of this. Say we want to determine the reactionary forces at A and B for a steel bar as shown below. The modulus of elasticity is taken as 200 gigapascal. And we have 300 kilonewtons applied at point K and 600 kilonewtons applied at point N. Now, the cross-sectional area of member AC is 250 millimeters squared, and that of CB is 400 millimeters squared. The lengths of member AK and KC are 0.150 meters, and that of CN and NB are also 0.150 meters. For us to begin, we are going to recognize that our reaction at B is redundant. So we will remove the support and calculate the deformation of the member due to our applied load. This is shown in the middle configuration. Then we will calculate how much force RB has to apply to counteract this deformation. This is shown in the right configuration. For our system to be compatible with the original configuration, we have to say delta AC plus delta CB plus delta RB is equal to 0. Now, for us to begin, we will remove our support at B and determine the deformation based upon our applied load. That is, we can say the deformation of member AC plus the deformation of member CB would be equal to the sum I is equal to 1/4 of R sub I times L sub I per A sub I times E. Now we note that there are 4 unique deformations we have to calculate. For the internal reactionary forces in member AK, KC, CN, and NB will differ, as well as their cross-sectional areas between member AC and CB. For us to begin, we first have to determine our internal reactionary forces, and we will do this by cutting member AC between A and K. In doing such, we find our internal reactionary force R1 is equal to 900 kilonewtons. This is valid in member AK. Next, we will cut member AC between K and C. And in doing such, we find our internal reactionary force R2 is equal to 600 kilonewtons. This force is valid in the region from K to C. Next, we will cut member CB between C and N, and we also find our internal reactionary force is equal to 600 kilonewtons. This is valid between C and N. Lastly, we will cut member CB between N and B, and we find our internal reactionary force R4 is equal to 0 kilonewtons. Thus, we can say our deformation of member AC is equal to delta AK plus delta KC. Now, member AK and KC each have a length of 0.150 meters, each has modulus of elasticity of 200 gigapascal, and each has a cross-sectional area of 2.50 e to minus 4 meters squared. Now, in member AK, we have R1 existing, and in member KC, we have R2 existing. Thus, we can say delta AC is equal to 0.150 meters per 200 gigapascal times 2.50 e to minus 4 meters squared times the quantity R1 plus R2. Now, we can do the same for member CB, and this is equal to delta CN plus delta NB. Now, CN and NB both have a length of 0.150 meters, each has modulus of elasticity of 200 gigapascal, and each has a cross-sectional area of 4.00 e to minus 4 meters squared. Now we have R3 acting in member CN and R4 acting in member NB. So we'll take our coefficient of 0.150 meters per 200 gigapascal times 4.00 e to minus 4 meters squared times the quantity R3 plus R4. In doing such, we can calculate the deformation of member AC, and we find it to be 0.00450 meters. Likewise, the deformation for member CB is 0.00113 meters. Thus, our total deformation is 0.00563 meters. Now, we have to apply a force, RB, to recompress our system by the same amount that it has deformed. That is, we can say delta AC plus delta CB plus delta RB is equal to 0. In this particular configuration, we do not consider our applied loads at K and N. Rather, we'll solely look at the effect of our reactionary force at B on the deformation of our system. For us to do this, we have to first determine our internal reactionary forces as we did previously. That is, if we cut member CD, we would have R5 existing internally, and if we cut member AC, we'd have R6 existing internally. Thus, we can say delta RB, which is equal to the negative of delta AC minus delta CD, which is minus 0.00563 meters, is equal to 0.300 meters per 200 gigapascal. For members AC and CD have the same length of 0.300 meters and the same modulus of elasticity, times the quantity R5, our internal reactionary force existing in member CD, per the cross-sectional area of member CD, which is 4.00 e to the minus 4 meters squared, plus R6, which is the internal reactionary force in member AC, per the area of member AC, which is 2.50 e to the minus 4 meters squared. We note from our free body diagram above, the R5 is equal to R6, and both are equal to minus RB. Thus, we can say minus 0.00563 meters is equal to minus RB times the quantity of 0.300 meters per 200 gigapascals times the quantity 1 per 4.00 e to the minus 4 meters squared plus 1 per 2.50 e to the minus 4 meters squared. Thus, we can solve for RB, and we find RB to be 577 kilonewtons. Lastly, if we apply our equilibrium equations in the y direction, we can solve for our reactionary force at A. That is, we can say the summation of forces in our y direction, i.e. our vertical direction, is equal to minus 300 kilonewtons, minus 600 kilonewtons, plus 577 kilonewtons, plus RA. And we find RA to be 323 kilonewtons.